Okay, so we should start for the lessons today. Yeah, we're going to talk about the microcontroller platform for the Internet of Things applications and why we need a microcontroller in our system. Yeah, so right now you have a Python source code running on your PC, and your PC is a microprocessor unit. Yeah, the MPU. Okay, and a microcontroller platform is connected to your PC. So firstly, talk about the difference between the microprocessor and microcontroller. Okay, so yeah, when we consider the shape of the microcontroller and microprocessor, we're going to see that this is the microcontroller. Everything is integrated in a package. Yeah, it means that the memory, like the RAM memory, the ROM memory, the CPU, and all of the I/O, they are all integrated in a package like an IC. Yeah, it is. Normally we call this is an IC. Okay, so this is the microcontroller. And the microprocessor, it is like your PC when you can see the RAM memory, the HDD, peripherals. Yeah, the I/O, we have another name of the I/O, which is the peripherals. Yeah, when you can upgrade, you can plug in or plug out the I/O. Yeah, this is the microprocessor unit. So like this is your PC and this is the microbit platform. Okay, so this is the first thing when we talk about the microcontroller and microprocessor system. Yeah, everything is integrated in a microcontroller unit, but like your PC, the microprocessor, yeah, we need to plug in some peripherals like the RAM memory, some external memory, and some input and output. And the second thing, because everything is integrated in a package, the the microcontroller is very stable and reliable. Yeah, it can work 24/7. Yeah, everything is very stable, reliable with the microcontroller. However, our PC, it is not really reliable. Yeah, like when you turn on and turn off the power supply, maybe the memory, the external memory or the operating system can be broken. And this is the disadvantage of the microprocessor unit. Yeah. Your PC is a very good device for studying or for researching, but to release the system and run it on the field, microcontroller is much more better because this is more reliable and durable. Okay. One more thing, microcontroller is very cheap when compared to the microprocessor unit. Yeah, because everything is integrated and everything is optimized. The resource in the microcontroller unit, somehow it is a very small resource compared to the microprocessor unit, but it is enough for other applications. And so the price of the microcontroller is very low compared to the microprocessor unit. Okay, but now today we have some system. It is a combination of the microcontroller and microprocessor, like the Raspberry Pi platform. Yeah. Normally you have the operating system for the microprocessor, but you don't have the operating system for the microcontroller. Like you flash everything in the microcontroller when you want to transfer a program to the chip. Yeah, but here you install an application. Yeah, we have the operating system for the processor unit. Okay, so the Raspberry Pi, you have the operating system. Normally this is Debian or versions of uh, Linux. However, you have some interface to connect directly to the hardware or the pins of the system. And this is the next point when we compare between the microcontroller and microprocessor. Yeah. In the microprocessor, you can directly connect to the pin, and you can access to the memory of the pin. Yeah, but for the processor, you can't, because you are in a very high level, okay, higher than the operating system, and everything is controlled by the operating system. So it means that with your PC, you cannot turn on or turn off a light, but it is very easy, and like blinking an LED is the Hello World applications for the microcontroller. Very easy for the microcontroller to turn on and turn off a pin. Okay, so just compare between two programs. You have one, this is the parent source code, and second one, this is something you have on the microwave platform. Yeah, and when you need to control an LED, even you want to turn on it for 1 second and then turn off for 1 second, it is very easy for the microcontroller, but it is impossible for the microprocessor. Even your PC is very powerful. Firstly, you cannot turn on or turn off a LED, but if there is a mechanism for you to turn on and turn off an LED, you cannot make it precisely turn on for 1 second. Is impossible for a system which is based on the operating system. Yeah. When you need to turn on an LED, it's just a command sent to the operating system, and the operating system will arrange when the resource is available. It will execute this task, and it does not guarantee that the task gonna be executed immediately and exactly for 1 second. When you try to perform an instructions which is higher than the operating system, this is a task, and the task gonna be buffered in a queue or in a list, whatever. And after that, the operating system will execute them step by step. So it does not guarantee that when you need to perform a task, this task can be delayed a little bit. And if the task is concerned to the time or a duration or period, yeah, the operating system does not guarantee it as well. Yeah. Maybe the time for the LED is a little bit higher than 1 second, but it is not exactly 1 second. So the last point concerning the keyword, which is the real time. We say the microcontroller is the real-time platform, but the microprocessor is not real-time. Okay, so many difference between the microprocessor and the microcontroller. So firstly, I would like to summarize that many different points. Firstly, everything is integrated in the MCU in a small package, so that it is very durable and reliable. The price is also very cheap. With the microprocessor unit, you can upgrade the I/O, the peripherals, like your RAM, your secondary memory. You can upgrade. However, because they are not integrated in a package, they are not durable and reliable, and the price is also very high. Okay. Secondly, microcontroller unit, it is a real-time system, and microprocessor, it is not real-time because it has the operating system. The operating system is firstly the disadvantage of the microprocessor system. However, we have an advantage of the operating system. When you have the operating system, you can connect to the network easily and access to the internet service very easy. Okay. So because of this reason, you have the gateway, and we have the gateway. It has to connect to the network, and it also needs to perform some controlling task. So this is the reason why we need to combine the system into one. So because of this reason, I propose an architecture that you have a microbit platform and it is connected to your PC. Your PC is here very powerful for processing, for AI inference, for internet connections. And the microcontroller, it is very powerful for sensors, for controlling a device, for radio communications. Yeah, this is the next target in our system. Radio communications or wireless communications. Okay, yeah, very important information for you to distinguish a microcontroller and microprocessor, and please use it correctly. Yeah, sometimes you would like that you use the microcontroller to connect to the internet. This is also possible. Yeah, right now we have some modules and it can be connected to the internet service. However, yeah, the connection is not really reliable because the network is always unstable and the signal can be very low, or sometimes it is very high. Okay, so if you don't have the operating system, you have to manage the risk. And if the mechanism is not really reliable, yeah, the network connection can be disconnected. Okay, yeah, so if you have any questions, you can type in the chat. So this slide is used to remind you of previous course. Yeah, you do have the course concerning the microcontroller processor, the microcontroller system. Yeah, a device which is used to control an IC which is used to control a device. Okay. Okay, and when you need to design a program for a microcontroller system, yeah, you should follow the structure of C and C++. This is very important to structure the program in a microcontroller unit. Yeah, before this semester, yeah, normally you have to use the assembly to program the microcontroller. So the structure of your program is very cool. But just the previous semester, we used the HCMUT to generate. Yeah, we generate some source code, and the source code is in C and C++. So that's the structure is quite very good. Yeah, and very easy to improve. But this slide is used to summarize for a module you design in a microcontroller unit. Because the system is very low resource, yeah, you need a good architecture to control everything. Yeah, it is somehow a very simple image of the operating system. When you work with the microcontroller, even it is used to turn on or turn off an LED, yeah, you also need a structure. So this is the structure of the header file. Yeah, if not defined, you define because you want to include the header file. So to avoid duplicate problem in the compiler of C, yeah, you need this keyword. And after that, you need to input some libraries for your source code. Okay, this is some very basic steps. You need to develop something. The next one is, I don't know if you normally work with this one. You use the keyword extern to declare that what can be used by other modules when you input the LED module here. Okay, you can have more than 2 variables, but they are all declared in the CBP file, and you extern in the header file. You can see you have 3 variables: T on, T off, and counter. but you just extend TRIschien and TF. So like you provide two interface for other modules when it includes the header of the LED module. Okay, so like the private and the public properties when you work with Java or any OOP programming language. Even this is in C, we also organize like the OOP programming language. Similarly, with the properties or the variables, you have some functions, okay, and you also have the public functions and the private functions. Set on or set off, this is the interface you provided in the LED module. But inside the LED module, when you need to implement these functions, normally we call these methods, you need another function. Maybe it can be the delay, okay, but you don't allow other modules to use this function. So you make it privately in the CPP file and you public by a prototype declarations of the functions. Yeah, a very basic structure for your C program when you need to work with the microcontroller. Okay, so right now with the microcontroller, maybe it is very simple and you only have one file, so you don't need to structure anything. Yeah, you only have one file, but you need to design your program in another way. We're gonna talk it later. It is a kind of state machine. Okay, but if you work with a platform and you need to structure in C language, this is a very good approach for you. So when all of the modules in your program is structured like the header and the CPP files. In the main file, you just need to include these modules. Maybe you also need some libraries, but normally you just need to include your modules. All right. And at the beginning of the main functions, you just init one of them. And you start the main functions with an infinite loop, which is the while true here. You see, and you do nothing in the main functions. Normally in a microcontroller, every work are going to be implemented in the timer interrupt. Okay, this is the point. Yeah. You can implement your task in while true. You can, but normally we need our processing is started with the timer interrupt. Yeah. And we have a lot of interrupt service routine in a hardware platform or a microcontroller platform. It can be an external interrupt, it can be an ADC interrupt, it can be DMA interrupt, a lot of interrupts in the microcontroller platform. And yes, with a modern approach, right now you can implement a state machine in a while true, and from the timer, from the interrupt service routine, you set the state of your system. Okay, when you receive a signal, you set a state, and you process it in the while true. I don't know if you have any experience when you work with these programs. You can type something in the chat message. Okay, you need to implement a kind of state machine. You can implement it in a timer interrupt because it is repeated, right? Like you declare a timer interrupt with the counter is 10 milliseconds. So everything in the timer interrupt service routine gonna be executed every 10 milliseconds. So the behavior is very similar to while true, except that while true is forever and forever, and there is no delay. But there is a little bit delay for the timer interrupt service routine. But the behavior is almost the same. Yeah. Whatever you have in the while true or you have in the timer interrupt service routine, going to be repeated forever, right? Yeah. So while true and timer ASR, they are almost the same. You can implement it here or here. It's going to work. Okay, so this is an image of a state machine. So for all of your system, when you need to implement something, you can model your system using the final state machine. Okay, so in the slide, this is a kind of a turnstile. Okay, you can see it in the gas station, for instance. Normally, you have two different steps for this system, which is the lock and unlock. Yeah. When you stay in a lock, you execute something to block the rotation of this one. And when you are in unlock, you have your task. So normally you need a state machine when it is very clear to us that a shape of the system, it has a specific task, okay, and it has a condition to turn from this state to another state. So like when it is in the lock, you have a coin, you're gonna move to the unlock, okay, and when you push from unlock, when you push, it come back to the lock. Yeah, so this one is the condition to change the state of the system. Okay, and it is not really important conditions. Yeah, when you are in the lock, when you try to push it, it's still in the lock. Yeah, and when you insert a coin and it is in unlock state, you put another coin, it's gonna be in unlock state. Okay, and it stay in the unlock when if you put one more point. So basically the push here and the coin here, they are not really important and you can remove from your state machines. You don't need to implement these conditions. Okay, just the condition which is change the state of the system is required to implement. Okay, and all of the problem can be modeled by using the state machine. Right? All of the problems can be used the state machine to execute. Okay, and when you do have the state machine, your program is very easy to implement. Yeah, so you can see. Yeah, this is some proposals code for you to implement a state machine with two different states. Yeah, the lock and unlock. When you are in the lock, yeah, you just do your task. Yeah, when you are in the first step, which is the lock, you do your task. When you are in unlock, you do your task. And you don't care other things. Next, you need to implement the condition that's going to be changed from the lock to other steps. And from the state machine before, we see that there is only one condition need to be implemented, which is changed from the lock to unlock. This condition. Okay, so you're gonna have an if statement. You are in the lock, and if there is a coin, you change to the next step, and that's all. Because there is only one condition in the lock status, which is need to implement. Okay, So you have the second step of the system, which is unlock. You do your task, and when there is another condition, you move to the next step. And this process is repeated forever. Okay, so look at in the source code, you're gonna see that the coil and the push gonna be implemented in the hardware layer. And we say this is a layer, and it is belong to the firmware layer of the system. You are here in the finite state machines, which is a little bit higher than the firmware layer. Yeah. In the firmware, you're going to work with the device driver. Okay, you have to declare a variable, which is the coil. And if there is a real coil which is inserted, you set it to true. And if there is not a coil, you set it to false. And similarly, for this one, it is just a variable, but it's going to be linked to the real hardware, and it is the firmware design of the system. When you work with the state machine, yeah, they are like the software components. But from the state machine, it is very easy for us to distinguish that what is the software and what is the firmware or the device driver. And the coil, the condition here is the device driver. And the push here is also the device driver, which is implemented in the firmware layer. And after that, when everything is tested, you can switch to the finite state machine to implement the state and the condition to change the state of the system. Okay. Okay. So we move to another example, and we're going to use the state machine to implement this behavior. This one is very similar to the task in lab number 3. Yeah, but in lab number 3 you implement in Microcontroller, and somehow it is a little bit difficult for you at the beginning, but it is very similar to this example. So in this example, I would like to turn on the lab for a period and then turn it off. Okay, we do have some firmware instructions. So like I said, when you need to turn on an LED, you need an instructions, and it is the firmware instructions of the system. Like here you use digital write. Okay, it is not really important, but yeah, the main functions we're going to use to turn on and turn off the LED is digital write, and I just need this one to design this program. And this is the state machine of the system. Yeah, we do have 3 different states: the init, let on, and let out. Very easy for us to see that the system have LED on and LED off. Yeah, this is 2 basic steps of the system. But normally we have an init status just to init the hardware platform, or init some variables. Okay, and we change unconditionally to let on. Okay, there is no condition when we move from init to LED on, but there is a conditions for switching between on and off here when the timer is expired. Okay, when the timer is expired, we change the status of the system. So like in the last requirement of the lab number 3, you set the first information, and after that 5 seconds you set the second one, and the process is repeated every 5 seconds. So actually you have also 3 different steps: the init, set temperature, and set the light, for instance. Exactly the same state machine of this example. Okay, and we're going to try to implement it in the Arduino language, which is based on C. and after that we can switch to the block-based language. How we can implement this step machine in block-based language. I would like to stop my presentation a little bit and open the notepad to present some source code for you. Okay, so this is just an example how we implement a step machine using the Arduino source code. Alright, so in the Arduino you have the setup functions and you have the loop function. Right. Firstly, and it is related and forever by the loop functions. And normally in the loop function you need a delay 10 milliseconds at the end. Why? Because in the hardware platform, normally you need a timer to control the device. You turn it on for 1 second or turn it off for 3 seconds. You need a timer, and to simplify the process, I would like to put a delay for 10 seconds. And you're going to see how I implement a timer by using a very small delay. So actually, I'm going to use a variable. Okay, so I declare a variable over here and it's 0. So I need a status. Yeah, is a variable to keep tracking status of the system. And in the main source code of the loop, as good status. So very easy. You have 3 different steps of the machines. 2 different steps, right? You have 3 different steps, and you're gonna have 3 different cases. So in right, and you're gonna have a case on the track, and you have a case let off. And here's of the syntax. You should have the default mutation. Some steps which belong to the list. Yeah, you should have the default and bracket here. Alright, and this is the first step when you need to implement a step machine. The nice thing when you design your system according the very nice things when you design your system using the step machine is that you can implement any one of them. You don't need to implement the init and let on and let off. You can start to implement the let on. So like here, I do my task in this step, which is the right. Sorry. Because this is the step LED off, right? I do my task, and the condition to move from let off. Yeah, we have only one condition to move from let off to let on. Okay, and the condition is when the timer is expired, and this is when it is equal to 0. The timer is expired, and I move to. But if the timer is not expired, I try to count down the counter. It is very important functions. Yeah, it's like you update the timer. Okay. Yeah. Okay, status gonna be equal to let on, and you need to set the counter for let on step. Like you want the LED is turn on for 2 seconds. So the value you need is 200 because you have a small delay at the end. Okay, so like everything of your source code is executed very quick, and we have a small delay here. So like every 10 seconds, your source code is executed. And if you need a timer which is 2 seconds, you need to count out from 200 to 0, right? Yeah, because 200 multiplied by 10, it's going to be 2 seconds. Okay, so I can implement the LED on with this digital right. Yeah, I do my task. I do my task, which is use the counter. And if the counter is equal to 0, I move to the LED off. And I set the counter for the offset, and like I would like that and be off in 3 seconds. Right? And for the sorry, in Arduino, this is the Arduino. Okay. And system instruction can change. I set the color. I set the color for video and status. We don't have any conditions to change the status in the init. You have it like here. So this is the source code when we need to turn on and turn on LED. And you can see with the state machine, you only need variables and if statement. You never need a loop or a for or a while. You never need that. And in your source code, rarely, very rarely, you use the nested if. Normally the if is just like this. And you have another conditions. Whatever you have, you will have another if, and you have something to change this numbers. You don't need the nested if. So when you don't have the nested if, your program is very easy to follow and very easy to understand. And for other students, when you work in a group, you can split your task into some steps. Yeah, the first student going to be implemented. The second one going to be implemented with some other steps, and there is no conflict when you combine the source code. If you can design your system using the state machine, right? Okay, so if you have any questions, you can raise your hand. Okay, so this is the best way for me to check is that you open the method and implement the extra point of the last number 3. Yeah, so please open the method.microbit.org and you create a new project like PHC IoT and come to me by number 1 if you are ready in this window. Okay, so please confirm to me by number 1 if you are ready in the block source code. Yeah, I will give you some help in the extra point. Okay, so yeah, if you use the delay, you don't have the extra point. Yeah. If you use the delay, you don't have the extra point. There is no minus, just 0 or plus. Okay. Okay, so this is the structure I need you to follow when you design the state machine in block-free language. Yeah. The on start is somehow very similar to the setup functions in the Arduino. And if you have the init state, you don't need the on start anymore. Okay, in the forever, it is the loop function in the Arduino. And in my previous example, I used the delay 10. Yeah, and you can also use like, but this is 100. Why we cannot set it to 10? Because the hammer in the microbit is not easy correct if you set it to a very low period, because the block-free language is a little bit high level. Yeah, it cannot execute a very small delay, but the 100 is okay. It's acceptable for us to use the pulse 100 at the end. Yeah, yeah, you can use the pulse 100 milliseconds at the end. So next, we need to declare a variable, which is the status and the counter, right? The status and the counter. Okay, variable. You make a status, you make counter, right? Yeah, because in the block-free language we don't have the switch case, so we have to use the if else. Even I don't really like that we use the if else to characterize the status of the system. Yeah, I think you comprehend the principle of the if else and the switch statement. And the switch is much more optimized than the if else in this case. Okay, but we don't have, because we don't have the switch in block-free, we have to use the if else. And this is in the logic. Okay, logic. Yeah. You put it here, and because we have three different steps, so you're gonna have three if and else. So you just click on the plus here, you have 1 2 3, and then delete the else because I want to compare exactly the value of the status. So I make three conditions and then remove the else part, and I have this structure. Okay, confirm to me by number 2 if you are already here. This is just how we can use a tool. Yeah, programming language is just a tool. When you can declare a variable, when you can use the if statement, so it is like you are master 70% of the programming language. Is it okay? So please confirm to me by number 2 if you have the if, else if, and else if, because we have 3 different steps. Okay, so when you have these conditions, we will construct the conditions. Okay, so here we have 3 different steps, so we need a comparisons here. When the step is 0, 1, and 2, so I will copy the condition and I put it here, 1 and 2. Okay, the first here, which is the status, the first operator, which is the status. Yeah. So confirm to me by number 3 if you can construct 3 different conditions. So we use 0 for the init step, 1 is to send the temperature, and 2, which is the step that you send the light intensity to the gateway button. Okay, 3 different steps. Confirm to me by number 3 so that we can continue. Okay, so we start to implement more. Yeah, when the status is 0, we need to init the system. So like we set the counter. Yeah, we set the counter to 5 seconds. So this is number 15. Okay, if you want to make the delay for the status, the first step, yeah, which is 5 seconds. So this is 50 because you have 100 here. Okay, and you change the status. You change the status to 1. Yeah. You have the list here. Okay, and you can select the status. Yeah. In the init stack, you set the counter and you change the status to 1. Okay, in the status number 1, you count out the counter, and the counter statement is change counter by -1. This is the countdown. Okay, and so if the counter is equal to 0, if the counter is equal to 0, you move to the next step. You set the counter and you do whatever you want. Okay, so if the counter is 0, means that the timer is expired. You move to the next step. Yeah, you set the counter and you send the value of the temperature to the gateway. And you implement everything in this second if. Okay, yeah, so you can implement by your own and you share to me the link. You click on the share icon here, you publish your project, and you're gonna have a link, and you send your link in the chat of our meeting, and I will correct for you. Okay, yeah, so this is the structure of the program, and we don't use any delay or any loop in our source code. You're going to see this is a very useful structure for all of your project and all of the programming language. Yeah, for Python, for C, for Blockly, even for Java, I use this structure. Yeah. When you need to update your system, you just need to design again the state machine. When you need to add an extra functions, you can model your system by using the state machine, and you just extend the if here. If you have another state, you just update to your state machine and everything will be work. Okay, so continue for your implementations and share to me the link. Yeah, and I will check it for you. Hello? Do you have something? Or you can share your screen if you want. No. Yeah, you send the temperature value and you send the light value to the gateway. Yeah, we are working in lab number 3. The extra function in lab number 3. Okay, this is the LED turn on and turn off anymore. For my example, this is the LED. Yeah, but now you can improve to the extra point in your lab. Yeah. You also have 3 different states of the machine. The first one is the init. The second one is used to send the temperature value to the gateway. And the next one is to send the light value to the gateway. Okay, also 3 different steps. And you need to implement your task in every step of the state machine. Okay? Yeah, please try. And if you have something you need my support, you can share your screen or you can share your link. Okay, and I will correct directly in your program. And because this is the extra point, yeah, so please try. Okay, Long, what do you have right now? Okay. So I will check it very quick. Yeah, I will share my screen. This is your source code. Okay. Yeah, that's right. Yeah, this is your extra point. Okay, this is the task in step number 1, and this is the task in startup number 2. Yeah, correct. Okay, there is an error. You need to set the counter to 50 before you can move to step number 1 instead of step number 0. Okay, you move to 0. It is also okay. Yeah. But if you move to 0, it goes to 1 immediately. Yeah. So it is also okay if you set it to 0 here. But it is better that you set it to 1. Yeah, because you send the time 5 seconds, you send the light, and after that 5 seconds you send the time. Okay, so you switch between 1 and 2. We just need the init once. Okay, the startup number 0, we just need to execute once. So because this is the init, yeah. It is better if you can set it to 1 and set the counter to 50 here. Yeah, very nice. If you want to check, you can show a number here, show number 1 and show number 2 in the if, and you will see, yeah, every 5 seconds the number is displayed in the screen of the microcontroller. Yeah. To debug, yeah. After that 5 seconds, it switched to number 2. 1, 2, 3, 4, 5. Because the simulation is a little bit delayed, so we have to wait a little bit. But if it does not switch to number 2, you need to check your program. But I think it is okay. Change the counter if the counter is equal to 0. Change if if status is 1, change counter if counter is 1, show number, set counter, and set status to 2. Yeah, this is set instead of change. You see, you need to set 2. Yeah, and we need to run it again. One, and after that, yeah, just by debugging you can have some error. Okay, and it is 2, and after that 5 seconds it is 1 again. Okay, so thanks Long. You can update your program and confirm to me if everything is okay at your side. Okay. Yeah, even it is simple. Yeah. If we don't implement, we don't have these skills. Yeah. To have some bugs in your source code is like a normal things. Yeah. Even we write some 2 or 3 lines of code, we can have some bug, and we need to debug. And when you can debug your program, you have the experience and you have the skills. We can say, we can propose the idea, but you need skills to implement your idea, right? C, Blockly, Java, any programming language, it's just a tool. Yeah. It's just a tool. So the tool is easy to use at the beginning, or it is not really easy to use. Finally, the problem is the same. If you don't have the skills to implement and to debug. So in the state machine, it is very easy for you to follow the executions of your system. You just need to show the status, just to show the status on the screen or any devices. You can follow where it is. Okay, so like when I debug the program from long, just number 1 is shown in the screen. So that is some error in the status number 1. So you just need to check what do you have in the step number 1. So long, please confirm if everything is okay for your source code. Okay, I share the source code again for you to have some reference, but please work at your site. Alright. Even the source code is a little bit long when you have the state machine, but there is no problem for a program which is very long. Because if you use the loop, the execution is the same. Yeah, the execution is the same. A very long program, it just have one disadvantage, is that the size of your program is a little bit bigger when you transfer the hex file to the microbit. But there is not a problem because right now the memory is very cheap and the source code is just few kilobytes. Yeah, and memory is 100 megabytes, much more than your source code. So there is no problem. So we don't really need to optimize the size of the source code. What we need is to structure the source code in a way that which is very easy to debug, very easy to improve. Yeah. So like I want that you need to add one extra function like to control an LED. You just need to implement the second state machine and you put everything in forever. And the idea of the state machine is that at a given time, just one of the steps is executed. So imagine that you have another state machine for the LED, and it is like this one. You put everything in the forever, and at a given time, one state of the machine of the LED is executed, and one state of the sensor machine is executed. And this is the principle of the operating system. This is the round robin operating system. Okay, I can make it more readable. I put everything in the functions. Okay, I make functions. So like LED DFA. Okay, put it here. The delay here, I remove it. It is already removed. Okay, this is the state machine of an LED, and this is the state machine of I make a function, and you put it sensor EMA. Okay, and in the forever pause 100 milliseconds. In the forever, I call let DFA and sensor DFA, and you have like the operating system. And these tasks, like, they are executed parallelly, because it's gonna go to the first step, one step of the LED very quickly. It moves to the first, it moves to another step of the sensor DFA, right? DFA is finite state machine, finite automat. Yeah, it is another keyword for the state machine. And you can make a lot of DFA for your source code. And if you want to use it, you just call your function in forever. And you will see that even you can change the order, everything will be executed correctly. Even right now in the forever, the programming is not really in an order. You can call whatever you want. The parse function is just one of them. Okay, this is the idea to implement the round robin operating system. So now you have a very simple operating system on a microcontroller, and because you control the time, yeah, normally we say this is real-time operating system. Real-time operating system. Even it is not really exactly, yeah, but this is some basic step to implement a real-time operating system. Yeah, because the time you execute this one is like 0 milliseconds. Yeah, very small compared to 100 milliseconds. So the time constraint is very high in this scope. Okay, and this is the way to construct a real-time operating system.